for the organizer to inviting me on this very important meeting and give me possibility to say about the wave and the moving clothes and the frozen channel. That is a frozen channel. That is not only so romantic view like you can see, but it is also that is a ice tank in the some institute. For example, here that is a picture of the Antarctic Research Institute in St. Petersburg, and you can see the parameter of this ice tank, and they produced ice thickness of, from 1 centimeter to the about half of meter. And so experiments in the ice tank is very important, and we will consider the rectangular ice channel that is exactly like in a lot of the ice tank in the around of the world. And here you can see the coordinate of the system, and we will consider the three problems. One of them is the wave propagation along of the channel. That is the sloshing and propagating wave, because the wave propagate according to the x-axis, and they also we have like this kind of vibration across of the channel, the sloshing vibration. And another problem that is the moving loads is like a steady problem. When the loads move constantly with a constant speed along of the channel. And another one that is the unsteady problem when the loads initially at rest, and after that they move with a constant channel, constant speed. And here that is actually two sources of the previous results about this problem. One of the huge sources is about plate of infinite extent. That is the first work which we know, maybe very first was before. That is the papers of Haysen, and he published the book, but it is in Russian. That is about ice. And another book that is which I wish to mention, that is the books of Professor Squire with co-author, which is produced like a handbook, and also that is a very nice review about all the work. After that, I mentioned that is a lot of people who work on this topic, but in different way. And sorry if I doesn't mention somebody who is sit here and work also about the plate of ice plate or the elastic plate of infinite extent. And also I wish to mention the two groups. That is one of group at the Professor Kozin. They produced the experiments in the far east of the Russia. That is other names is Pogorelov, Azhovskaya, and Zemlyak. And also the small group now in the Lavrentiev Institute of Hydrodynamics, and the Sturova and Tkacheva. His work is very close for us. And other source, that is the wave and loss in ice covered channels, rivers and channels. That is the bibliography and references. That is the smallest, much smallest ones, and about the wave of infinite extent, and I just show you some of them. And but in both cases, the motivation of this research was the safety of work at the ice, navigation and transportation. That is like transportation of some loads through the rivers and lakes, and another one by ice, and another one that is like landing and takeoff on the ice airport, on the floating airport, and something this. And also additional motivation for the reefs and channels. This is the flooding, and that means that we need to have a mechanical break up, and also influence ice on the dump across the channel in the frozen rivers, for example. And here I wish to show you that several slides about the huge flooding at the River Lena in 2007. And by the way, here that is pointed the Novosibirsk and Barnaul when we come. That is the two cities, my home, like a home cities, Novosibirsk, and cities Barnaul, the home cities of my co-author. And the River Lena, that is a huge river, about the 4,000 kilometers. They start from Baikal Lake on the south and going for the Laptev Sea in the north. And that is river definitely frozen during the wind. winter. And here you can see the 3 photos of this river. That is this photo is about 1 week or 10 days between one to another, and the first everything is frozen and under the snow, and just a blue line, that is the river which is covered by ice. The second one, that is after the melting, the snow melt and the water come for the river, and you can see deep blue around the frozen ice. But second one, third one is you can see the huge flooding, the huge area covered under the deep blue, because that is something happened, or maybe on the north part of the river, that is some damping through the ice, or maybe I don't know, maybe huge melting on the south. And so finally, that is according to Dartmouth Flood Observatory, that is along the Lena put 12 towns under the water and damaged and destroyed the 41 bridges and affected for the more than 14,000 people. That is very dangerous. So the question about how to break ice, how to operate with ice, how to protect with this flooding. This kind of flooding is very important. And that is, I say that is in far east of the Russia, that is a group of Professor Kodin, they work about the resonance method. That is here, that is from the internet page, from the Wikipedia about this method, and they say that is for the special phase velocity, that is water doesn't support the elastic plate. Maybe from mathematician point of view it is a bit different, but they explain this method like this, and that is they suggest use the hovercraft with a special velocity for the special ice. And actually similar ice breaking hovercraft was used in St. Lawrence River. They just also know that for the special speed that the ice will be break, and they by experiment, by his own habits, try to find this speed to break the ice. And also in the here I wish to show you the ice tank is the Shalom Aleichem Institute University that is in Birebidjan. They also try to produce to break the ice by the underwater body, splendid body, but also that this body must move with a very special velocity. And here I wish to show where is this institute located. That is a special Jewish autonomy in former Soviet Union that was founded 80 years ago. And now that is, but at least they have a university, they have a nice ice tank and provide some experiments. And another problem according to the frozen rivers and frozen channel, that is a dam breaking problem. Could you imagine that if you have several dams according to the river which was frozen, that is and what has happened if the first dam, that is the upper dam, is breaking, and we have some wave going down, and what will be happen here if the river or the reservoir was covered by the ice. By the way, in this paper, that is only unique paper, at least which we know, that the like a boundary element method was used for modeling the ice on the river. On other, at the same paper which I showed before, that about the river, ice-covered river, that is usually used as just a one-dimensional model of the ice. And also, there are some results, that is the results of Paul Bruckenhorst of his PhD thesis. He exactly considered the action ice and ice wave into the ice cover on the walls, or vertical walls. If the first problem, and another was a problem about the wall or the lack of the bridge or the platform, and that is very important. That is, if we have just a water wave, that is the vertical vibration of the wave doesn't too much affect it on the wall. But if it is a frozen, that is we have a vertical force on the wall, on the leg of the platform, and that is very important. And also, if we consider it the moving loads along of the wall, you can see. Doesn't work. You can see that is another kind of the wave, that is like a H wave, which is not on this part, only near the wall, and that is very important. And here I just announced the results to comparison the deflection. Deflection it is this part and strain this part for the ice covered channel, and the same conditions, but the infinite motion the loads along with the infinite extent. You can see that is a very periodic wave before the loads, and also I wish to point your attention for this very high strains and stresses near the wall, which is not appear for the wave of infinite extent. And so now we come for the mathematical problem about the wave on the channel, frozen channel. That is the problem is coupled. We have a hydroelastic part of the problem, which is just according to the earlier deflections, and with the clumped conditions. By the way, that is a similar problem, but with the free conditions was considered in this paper. And second problem, that is a hydrodynamic problem, and this problem is coupled because we have a hydrodynamic pressure when the velocity potential from the second problem put into the first one, and also that is the deflection of the plate come to the in the hydrodynamic part from the elastic part. And so we will consider the propagating wave when A is amplitude, the F is like a shape function across the channel, and the periodic wave along the channel, and the same similar periodic condition for the propagating wave. And after substitution of this presentation in this equation, we obtain that one. And this equation is quite nice according to the shape function, and we can solve this problem by the normal mode method and expand shape function on the series of the special modes. That is a dry modes, but condition is like a frozen conditions. This problem is relatively easy, but at least they give the analytical solutions, and we know it, and that the even and odd parts are separated in these solutions, and we have a shape, not shape, but normal mode at two normal modes, even and odd, present here, and also these functions satisfy orthogonality conditions. And substituting this expansion of our equation, and after integration, according to the orthogonality condition, we obtain some equation in the matrix form, and we have a two matrix. This matrix is can be, each term can be analytically found and presented, and another one like added mass matrix, because it is a connection between the hydrodynamic part and elastic part. And to solve it, we can find this matrix, solve the special problem, this problem that is which is an analogical of the our hydrodynamic problem, but with the special conditions, and finally obtain that is these terms, this matrix. And as a result, we have a matrix which is because we have enforcing additional force, that is the matrix is homogeneous, So we need determinant of this matrix must be equal to 0, and from this condition we obtain the dispersion relation, that is a shape function, and after that that is the group and phase speeds. And here that is I wish to show you that the results about the dispersion relation, that is the even and odd modes, which is one to another, and 2D waves for the wave of infinity extent at the green line. That is very important, that now we have that not only one dispersional curve, but we have a set of these dispersional curves. And that is a shape function, that is like a sloshing across the channel. And also I will show you what has happened if the condition is the free condition at the at the channel walls, and that is a dispersion relation go down. And we also find that is some simplified formula, which is the first formula for the first dispersional curve. Actually, that is the first term of this matrix A. That is the two terms for the second one, and give a very nice predictions. And for the free conditions, we obtain this approximation, and that is important. That if we take instead mu and k, we obtain the same curve, which is for 2D wave. And by the way, that is at least in our numerical conditions, that is 2D wave, and the first mode for the wave with the free conditions is the same. And now I turn for the phase and group velocity. That is for the first mode, under our conditions we have a long interval when the first velocity, first phase and group speed is the same, but for the others, like for the second group and phase speed, we have a lot of critical point, that is point with the critical velocities. And but on the other conditions, of course we have that as like usual, that is this limit, and first critical velocity is that one. And now here that this curve demonstrated that how the which of the channel is affected on the critical velocity. The critical limit is not the same actually like a square root from the GH, but quite close, but because the ice must be affected on this limit. But for the narrow channel, that is critical speed stay high with the same thickness of the ice. And as I tell you, that is a second problem. This is about of the moving clouds, steady problem about the moving clouds along the channel. And now we use the Kelvin void model because we need to take into account that at the infinity distance, that the wave must be decay. And we present the rods in the very smooth shape, that is with some radius, like a radius equal to half, the diameter equal to unit, and in the we will consider the problem in the moving coordinate system. And in this case, we need not only the normal mode, use not only normal mode method, but we solve this problem through Fourier transform, and after that the similar expansion, but now that this coefficient, the principal coordinate depend of the xi, and we obtain the system, a similar one like before, but now we have a vector p, which is obtained by this formula. Is actually that is a projection p on the function psi. And also for the velocity, no, not velocity potential, for the flow, we solve not the Laplace equation, we solve the Helmholtz equation. And finally, we obtain the solution in the matrix form, and but now that is not homogeneous matrix, so we can solve it directly. And now I will present results. That is here you can see that is the results for the three different speeds of the moving clothes. One of them is the 3 meter, is the low than the first critical speed for the further speed. Second one, 7, is above the first one, and the third one is above of the second one. And we can see that the three different, absolutely different behavior of the plate deflection. And this plot is for the deflection along the channel, that is across the channel. And we can see that for the first, for the under critical speed, we have just deflection, no, not according to the first mode, but closer for the first mode, for the second one, more closer for the second, and that is for the third mode. And also, it is interesting that in this case, the deflection of the eyes go before that is up to moving clothes, and for the last case, it is also a huge deflection after the loads. And here, results for the strains for near at the center of the channel and near the walls of the channel. And we can see for the case of the 7 meter per second that the strains near the walls is higher than strains near the channel, under the body, at the center of the load. Here we estimated which loads we need to use to destroy eyes, and what will be happened if we will move according to our critical speed. You can see that the deflections stay much higher than in previous one. The first one, the blue curve is the same like here. And also, that is for the stresses, again, that is a blue curve like this one, and red like that one, but stresses near the wall and at the center of the channel is very similar, very high. So that is a way, like a resonance method, when we can destroy it, just very small loads, not 400, but 21 kilograms, if you move along of the channel with this speed. And also, we understand how what has happened if the velocity of the loads is the 3 meter, that is under critical speed. We have only one curve, only one minimum, no any wave, because no other wave go along of the channel. If we have 7, we have one crossing of the farther speed. That means that the shortest wave go, but shortest wave have higher velocity and go upward from the, go forward before the loads. And for this case, we have a 3 crossing, and we have the long wave under the loads and the 2 short wave here. And we estimate that if the parameter tau is small, that the wave is more visible, but the length of this wave is exactly the same, which is predicted by this point. And here the similar results for the load which is moved under the ice. That is the results was presented in conference Polar Mechanics, that is 2 weeks ago, and they show that for the 3 different models in this velocity 2 meters per second, they have a maximum deflections, and so that the ice can be broken more precisely. Now we produce our calculations and find that the not for 3 but 3.5 meters, that is the velocity is 2.5 millimeters, is the velocity is 2 meters per second, and that is the critical velocity exactly, and the deflections along of the central line and deflections in our critical case but for the different conditions is quite similar. That is not periodic, not anything. And also I just demonstrate what will be happened if the moving load not on the central of the channel, but they move closer to the one of the wall, and that is the plots for the stresses, and we can see that if you move quite close for the wall, we have a very high stresses on the wall. And the last problem which was announced, that is a unsteady problem, and we need to when the load is at rest at the initial time instant, and after that they move with the constant velocity, we need to consider it behavior with a long time. And now we solve this problem not according to the Kelvin-Voigt, not viscoelastic model, but just for elastic model, and that is a elastic model for the moving loads, and pressure again depends on the hydrodynamic part. And the hydrodynamic part is also about the same, but now that is a connection between the hydrodynamic and elastic part, and now we have also initial conditions for this problem, and which is very important. And also, if we determine that the deflection, initial deflection of the plate, according of the these loads, initial loads, we obtain the very important parameter of the problem, which is named the characteristic length of the ice cover, and this parameter will be used for non-dimensional variable in this problem. And this problem was solved also through Fourier transform, and after Fourier transform we obtain this problem, and we had a elastic and hydrodynamic one, and to solve this problem we separate variables. Similar way, after substitution we obtain the following equation, and this equation, this separation can be done only if these two terms proportional one to another. So we arrive to the problem like eigenvalue problem with omega square like eigenvalues of this problem. And to solve this problem in non-dimensional variable, we obtain this equation. But actually, this equation, according to the function f, that is the same function f which was the first problem for propagating floating wave in the channel. And then this function satisfy for orthogonality condition. We will use these conditions, and after substitution series and after using orthogonality condition, we obtain the equation for the principal coordinate A. And we can find solution of this problem in this special form. But one can see that is for this value of the parameter omega, this problem has some singularities. But that is each term has singularities. This for the minus, but U, that is for the plus U, and that is for both cases. But by miraculous way, that is if we will consider it, everything all together, that is no singularity in this point. So we can substitute this problem, take inverse Fourier transform, and obtain the function, the deflection of the ice in this form. And this form is quite interesting, that this term is quite interesting. If we will consider it precisely, that is separate for the three terms. One of them like amplitude function, another one is a propagating Hloshing wave, which we studied before, and the blue one that is like cutting function, which is from one infinity it is equal to 0, and for another infinity it is equal to 1. So, as we considered before, if we, for example, if the loads moving with the velocity 25, no, with this velocity we have 3 crossing, and each crossing produce the wave. That one, the long wave on this side of the plate, and these two produced 2 waves here, and we can present all deflection in the like a combination of the just under critical speed loads, just like a steady loads, deflection under the steady loads, and that is a 3 wave. And it is in my point of view, that is quite interesting analytical results that we have can separate our problem for the like a previous one analytically. And no, that is the same results. No, that is similar results. I show you this plot before for the our for the second problem when we considered steady motion. Oh, thank you. But one moment, because I have a few time, I wish to show you what will happen with the leading model for the unsteady problem. That is, if ice is very thin, but we have a frozen condition, the leading model is about the unit, but 0 for the h. If the ice is thick, we have like no, not sinusoid, but the very smooth shape. And also, that is before. No, I have a 10 minutes.
Yes, you have
what will be happened if we will consider it not correct problem? If we will consider it our problem is hydrodynamic problem, we use the 2 terms in the right hand of this equation. But if we will consider it just hydrostatic problem without this term, without the motion of the fluid, even the model of the dry plate, we can see that the dispersional coefficient is very different. That is for full problem first and second. For the this approximation, that is much higher, and for the dry plate model, it is also quite higher. And the same big difference for the critical speed. That is very low for the not very low, but it is normal for the hydrodynamic model, but very, very high for dry plate model, hydrostatic model. And because the critical speed is very important for the moving loads or for the other results which was shown before, we can see that the difference even for the under critical speed, that is the dry plate model, when the plate doesn't support by the water, the deflection is much higher, only, but hydrostatic is close. But for this speed, which is above for the critical, that is we have this behavior of the deflection, but other model doesn't present this behavior. So that is it is very important consider the full model without any simplification. And so now second question.
Okay.
My first mother-in-law was Dutch, and she liked to skate in such a canal. And she, of course, she didn't believe there was critical speed, as some people suggested there was. I've got so many questions, but there was one slide you showed where you showed the wave pattern. You had the infinite regime, infinite plate, and then you also had the canal. And up front, it seemed to be that the flexural part was very strong.
Yes.
Is that an observation, experimental thing, or is that a theoretical?
Oh, that is
One of your
I think that is
slides.
a calculation according to this plot. If we have a viscoelastic model with a very small tau, we have a pocket here, and probably.
And with the wave pattern, can you go back? I think it was about the fourth or fifth. Can you flash back to that before you got to the analysis? Yeah, well back.
This one.
Oh, yeah.
Just.
Yeah. Sometimes.
Yeah,
Oh,
was this?
maybe there was it?
Yeah,
Yeah, there, that one. So there's your ice-covered channel as against the ice cover of infinite extent. And it looks like up front, where the flexural bit is, looks to be quite strong. Is there some reason? Or am I interpreting it wrongly?
The thing reflected off the walls.
Yeah, I'm
It's
thinking of the
striking out.
reflection. Is that the factor that? And have you looked
But
at that?
probably this wave satisfy for the.
The gravity part behind doesn't look very different, but that certainly does. And I'm wondering if that makes it more destructive.
for the steady problem,
Yeah.
and with the parameter of viscosity is very small. That is, we have like a long pocket.
One of the things I put into the to-do basket was to look at interference patterns, reflections and so on. Never got there. Has there been work done on that? Maybe Sasha knows. Huh?
No, maybe. No, we try to have a connection with the Birbidjan model basin and take the experiment according to our calculation, or take our calculation according to the experiment, and maybe in near future we will try to combine our results.
Still in the to-do basket. Okay.
Okay.
Thank you.
Just
No.
to answer. In experiment dissipation say parameter, damping parameter is very high.
Okay.
Yeah. So the computations and real life are different.
Okay. We talk again later.
About halfway through, you showed us some slides where you said that the strains along the edge were comparable with the strains in the middle, in fact slightly larger,
Okay.
in the direction of the channel. So that's a free situation, obviously.
No.
No, that is
Well, how can you
not
have
free,
strains
that is
along
a
the
frozen
channel
ice.
but not?
Oh, no,
It's
no.
curvature.
No, perpendicular.
Ah,
Yes,
Yes.
because it's a maximum.
But then it's
There are
still-
two of them. Nothing along the channel, but perpendicular, it's maximum. It's not zero.
on the edge.
Okay,
So
that is
It's not. It's clamped.
clamp.
How can it be clamped and have a curvature?
No, it's going to
The
zero.
curvature across the channel.
I know what a curvature is.
It's going to zero there, Ben, very sharply. Huge strain there.
I see. Okay, well, what I was going to ask is, have you calculated the stresses across the channel?
Yeah.
Yes.
Okay. Have you got that? Did I miss that?
Not here, but I will show. Probably I will show you later.
No, strains on the wall, they are across the channel. Because as you said, along the channel, they are zero.
Yeah. But I'm talking across the channel. I'd be interested to look at
In the middle.
Pardon?
In the middle. In the middle of this channel, or
No, at the edge.
No, that is across the channel. That is along the channel from
For the
Maxa,
clamp
but me
situation, I
along
would
the
like to
line.
know what the stresses are at the edge of the channel. That's my
In
question.
some previous presentation was like a 3D plots, and maybe that is possible. But I mean,
It would be very interesting to know, because it would mean that the ice was trying to separate from the wall.
exactly.
I convinced my mother-in-law.
Would be shocked to know.
And here you can see that is also that is a line which is broken, that is not exactly across the channel, but that is with some angle along the moving plot. So we probably we need to build that as like a map when the stress is at the highest, the direction. That is, in some near future, I hope we will do.
So that reminds me of Hong Tao's talk about the ice breakup in the springtime. The cover would release from the bank first before it breaks up in the middle. So maybe you can predict that square root GH, whether that's the critical velocity or less, to tell whether the bank will release or not.
Yes, that is probably that that is most predictable. That is less than this.
This is a question about not the walls, yes?
No, it's on the
that
top.
the stress is closer for the wall is maybe higher and maybe.
There is no walls on the river. There is
No,
But that is the frozen condition that is there on the plate.
It's
not
more or less
vertical.
flat surface. It's
not
not
vertical.
wall.
Not sure.
Okay?
Yeah.
Because in the rivers we're talking about long waves. And here it looks to me, it seems to me, if I understood, it's more on the periodic type of wave. Shallow water wave compared to this kind of wave you're looking at.
Yeah, the wavelengths are still
I can
even up front.
I can answer the results for shallow water are not sure, but they are published. And also this is what's interesting about the ice and channel, that for waves, two-dimensional waves in plate of ice on infinite extent, they are gravity waves for long length. So long waves, they are gravity waves. The bending is not important, but it's different for the channel, because for the channel there is another mechanism. The plate is kept on the walls, and this means even for long waves, they are not gravity waves.
This is
Means that is
Not
not
exactly
square GT. There is the factor, and actually the dispersion relation is not that one for gravity waves. There is this factor which depends on HGDT and width of the channel. So it's different, yeah.
So the ice you're looking at in the channel is frozen to the bank.
Yes,
Okay.
yes.
Yeah,
But it's not exactly. Sure, it's a simplified problem compared with the river, because the river there is complicated.
Let's not worry about the
Yeah,
complication.
but potentially it's possible to extend it to another shape. Potentially,
That's not important, I think.
yeah.
Okay. Okay. Thank you.